Hey guys, tonight we drift outward together into the dark, into that soft velvet sky you see when you look up from your window or your balcony, and we ask a very simple, very strange question. Is all of this moving? You see the stars as still points, quiet pinpricks of light, but tonight you find out that on the largest scales, nothing is really still at all. You imagine your body sinking into the mattress, your breathing slowing. Somewhere far above you, galaxies slide away from one another like tiny lanterns on an ever-stretching river. Astronomers a century ago began to notice this motion, not with their eyes, but with the colors of the light itself. They saw galaxies blushing slightly red, their light stretched as if space were taffy being pulled. You probably wouldn't survive being shrunk down to atom size and tossed between galaxies. But well, try it in imagination anyway, because in this story nothing hurts and everything is gentle. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Maybe write in the comments where you're watching from and what time it is for you right now on this tiny moving world. Now, dim the lights and let's ease into tonight's journey together. You lie there, and in your mind you travel back to the early 1900s, to observatories on cool mountaintops where mirrors gleam under dome roofs. Astronomers are looking at little fuzzy patches in the sky that people used to think were cloud-like nebulae inside our own galaxy. As your viewpoint settles beside one of these scientists, you see them feeding glass photographic plates into a telescope, capturing thin smears of starlight. On those plates, the light from distant galaxies is split into rainbows, spectra, etched as dark, delicate lines. Those lines are the fingerprints of atoms, each element leaving its mark at a particular color. But something odd appears. Compared to the same fingerprints measured in a lab on Earth, the lines are shifted. They're nudged toward the red end of the spectrum. The light seems stretched, as if it has been singing the same note for millions of years and slowly dropped in pitch. At first, people think maybe it's some local effect, a kind of cosmic weather. But as more and more galaxies have their fingerprints measured, a pattern emerges. The farther away a galaxy is, the more its light is shifted toward red. Distance and recessional speed rise together, like a gentle slope on a graph. This relationship becomes known as Hubble's law. Galaxies recede from us at a speed roughly proportional to how far away they are. You float above that graph for a moment, looking down at the dots that represent real galaxies, whole islands of stars. Each dot is a message from the past, light that has been traveling for millions or even billions of years, carrying news. I am moving away. The universe, it seems, is not a static stage where matter just shuffles around. The stage itself is swelling. In your mind's ear, you hear the soft clicking of the old telescope's clock drive, following the sky. The air smells like cold metal and dust. The scientist beside you is frowning, then slowly smiling, realizing that this isn't just motion, it's a new kind of motion. It's not like planets orbiting the sun or stars orbiting the center of a galaxy. It is the large-scale fabric of space itself, changing with time. A quiet question settles into you. If everything is moving away from everything else, does that mean there was once a time when it was closer together? The picture begins to reverse, like running a cosmic film backwards. Galaxies draw nearer, the universe shrinks in your imagination, and you approach a moment when everything you know matter. Light, even the structure of space and time, was compressed into a much hotter, denser state. That's the intuition behind the Big Bang model, later supported by the glow of the cosmic microwave background and other evidence. You may notice something comforting here. From your viewpoint, it looks as if all galaxies are fleeing you, as though you sit at the center of everything. But cosmology gently takes your ego by the hand and whispers, everyone sees it this way. To observers in a distant galaxy, you would be the one sliding away. Expansion is democratic. No single place is the center. Maybe the universe just loves to repeat that lesson. You are special, but not central. Important, but part of a wider pattern. The idea of an expanding universe was shocking when it first appeared. For a long time, many physicists preferred a static cosmos, frozen and eternal. Even Einstein initially added a cosmological constant to his equations of general relativity to hold the universe still, a mathematical anti-gravity to balance things out. When expansion became hard to deny, he reportedly called that adjustment his biggest blunder. though historians aren't entirely sure if he actually used those exact words. Either way, the feeling is real. Reality had surprised even the smartest minds. As you breathe in, you imagine those equations not as symbols on paper, but as a kind of choreography. Gravity curves space. Space tells matter how to move. And on the largest scales, that curved space can itself grow or shrink. When there's enough energy pushing outward, like whatever fueled the Big Bang, or the mysterious dark energy we'll meet later, the cosmic fabric doesn't sit still. Swaths of space stretch, like a slow-motion balloon inflating in complete silence. You might feel your own chest rise and fall, a tiny expansion and contraction in rhythm with your lungs. That simple movement becomes a metaphor. Inhale, the universe expands. Exhale. For a moment you imagine it could all fall back in. Of course, your breathing doesn't drive any galaxies, but it connects you emotionally to the idea that even the cosmos has a kind of history, a story with a beginning, a development, and somewhere ahead a fate. The most tender part of this realization is that every quiet photon entering your eyes right now has ridden this expansion. Its wavelength has been stretched by the growth of space, its color slightly softened by age and distance. The night sky isn't just a static wallpaper. It's the visible trace of a universe that has been changing for 13.8 billion years. Each star you see is framed by that invisible motion. Lying there, you let the thought settle. The expansion of the universe is not loud, not violent from your perspective. It is a kind of cosmic breathing, far slower than any heartbeat, a background rhythm that has been playing long before you were born and will continue long after you're gone. Knowing this doesn't demand fear. If anything, it offers a strange serenity. You are part of a story already in motion, a passenger on a ship whose sails are made of space itself. And as you feel your body grow heavier against the bed, you might think, maybe it's okay not to control everything. The galaxies move, the fabric stretches, and you are simply here to witness a tiny slice of it, in this moment, on this night. You're still lying there, feeling your body slowly settle, and now the darkness above you begins to change. You imagine the night sky not as a flat dome, but as a deep, layered space, like rain clouds stacked one behind another. Only tonight, the raindrops are galaxies. In your mind, you tilt your head back and watch as these glowing drops hang in the dark spirals, ellipses, messy little smears of light. Each one holds billions of stars, and yet from where you float, they look as simple as beads of dew on a window pane. Then something gentle and surprising happens. The space between them begins to stretch. The galaxies don't roar away like rockets. Instead, they drift, quietly, the way raindrops slide down glass when gravity is patient. You see lines connecting you to every galaxy, a web of invisible threads. As the cosmic fabric stretches, those lines lengthen. The galaxies follow not because they're thrust outward by an explosion, but because they're carried along by the growing fabric beneath them. To understand how we know this, you glide closer to one of these galaxies. As you approach, its glow turns into starlight, and that starlight turns into something even more delicate, waves. You imagine each wave as a tiny ripple in a cosmic pond, crests and troughs passing silently through the vacuum. The color of the light depends on the spacing of those ripples. Shorter spacing, bluer light; longer spacing, redder light. Now you shrink down in imagination until you're riding a single wave of light leaving a distant galaxy. At first, your wavelength is short, maybe bright blue. But as you travel through expanding space, you feel the distance between your crests slowly increase. It's not that you're getting tired, it's that the pond itself is being stretched. By the time you arrive at an astronomer's telescope, your once blue light has reddened. You've been redshifted. Down in that telescope's dome, an astronomer spreads your light into a spectrum, a smooth band of colors like a rainbow printed on glass. In that rainbow are tiny, sharp lines, gaps where atoms in stars or gas have absorbed particular colors. On Earth, in a laboratory, those same atoms leave their fingerprints at exact positions. But your lines are shifted just a little toward the red. That shift is the universe whispering, "I've expanded while this light was on the way." You, still riding that wave in your imagination, notice that the amount of stretch tells a story. A little stretch means the galaxy isn't receding very fast. A bigger stretch means it's speeding away more quickly. Redshift becomes a code, a quiet language that astronomers learn to read. When they measure the redshift of thousands, then millions of galaxies, They are really mapping the way the universe grows. You drift higher, and the view zooms out. Below you lies a vast three-dimensional map, dots marking galaxies, each colored according to its redshift. Some are nearby, bluish-white in your visualization. Others are far away and tinted a deeper red. The pattern looks strangely familiar, like a cosmic sponge or a lace of glowing filaments. Long strands of galaxies form where gravity has pulled matter together. Vast voids yawn between them, almost empty. This image isn't guesswork, it echoes what enormous surveys of the sky have revealed. Astronomers have spent years scanning huge swaths of space, measuring redshifts for galaxies and turning them into distances. When they plot all those positions, the universe looks less like a random scatter and more like a delicately woven structure. Filaments, walls, and voids stretch across hundreds of millions of light years. Even in the chaos, there's pattern. Maybe the universe really does love repeating its favorite shapes. As you hover over this map, you notice something subtle. The galaxies farther out, the ones whose light has been traveling the longest, seem to be moving away faster. Their redshifts are larger, the graph of distance versus speed. The Hubble relationship you visited before emerges not just from a handful of galaxies, but from enormous data sets, each point checked and rechecked. The expansion isn't a rumor, it's written into the colors of the sky. Now you imagine the galaxies truly as raindrops, not falling down but being carried outward on an inflating balloon of space. If you paint dots on the surface of a balloon and then gently blow it up, each dot moves away from every other dot. No dot is the center of the motion. The entire surface is stretching. That's what cosmic expansion feels like. Not things flying through space from a central explosion, but space itself growing between them. You picture yourself as one drop among many, our Milky Way drifting along on this stretching surface. Nearby drops our neighbor galaxy Andromeda. The members of our local group are close enough that gravity overrules expansion, pulling some of them toward us instead of letting them slip away. But zoom out more, beyond our local group into the grander web, and the expansion wins. The drops recede, the gaps widen, and the cosmic rain thins with distance. There is a quiet comfort in this image. You are not being flung away from everything in violence. You are part of a slow, graceful drift. The same physics that lets you understand a prism splitting white light on your desk is what lets you understand redshift over billions of light years. Light is light. Waves are waves. Whether they travel across a millimeter or across the universe. If you listen closely, there's almost a sound to it. Not a real sound, because space is mostly too empty for that, but a kind of imagined hush. Countless photons stretching, their pitches dropping beyond what human eyes can see, sliding into infrared, then microwave, then radio. A soft, cosmic sigh as the wavelengths lengthen, and the universe's light becomes older, gentler, and dimmer. You might wonder, as you watch these galactic raindrops drift apart, does this expansion change who you are? On your pillow, you don't feel longer. Your room doesn't suddenly loosen at the edges. And that's because, while space on the larger scales expands, structures like atoms, planets, and even galaxies are bound tightly enough by forces electromagnetism, gravity that they don't simply stretch along with it. The rain falls on a stretching window, but each droplet holds itself together. So do you. The night sky in your mind now is full of meaning. Every faint smudge, every speck, is not just some star stuff out there, but a raindrop on a moving window. Its light shifted, its history encoded in color. When you next look up for real, maybe you'll imagine invisible numbers hovering beside each galaxy, its redshift, its distance, the time its light has traveled to reach your eyes. It's like reading old postcards from a universe that has already changed by the time you receive them. You exhale slowly. The galaxies keep drifting. The rain, on these scales, never stops. And nestled inside one tiny raindrop, on a small rocky world, you are simply watching, feeling the gentle pull of sleep as the universe writes its story in shifting light. You lie a little deeper in the dark now, and the picture of drifting galaxies softens at the edges. The question rises quietly. If the universe is expanding, why doesn't everything just rip apart? Why doesn't your pillow stretch, or your hand slowly drift away from your arm, or the atoms inside you unravel like frayed thread? To explore this, you imagine the universe not as a collection of things in a box, but as the box itself changing size. You're no longer just looking at galaxies as raindrops. Now you're touching the glass they slide across. That glass is space-time, the fabric that stretches. In your mind, you float above a vast, grid-like pattern drawn in faint silver lines. Each square on the grid represents a region of space. At first, the lines are close together. Then, as you watch, the grid slowly swells. The squares grow. The intersection points where galaxies would sit move apart, even though they're not crawling across the grid at all. The grid itself is shifting beneath them, like ink dots on a balloon being gently inflated. You decide to test this idea on something familiar. Your room. You imagine that same cosmic grid superimposed over your ceiling, your walls, your bed. If the grid lines expand, shouldn't your room expand too? But now, zoom in. You see atoms in the walls, little solar systems of electrons bound to nuclei by electromagnetic forces. You see Earth held in its orbit by the sun's gravity. On these scales, the forces binding things together are strong enough that space can try to stretch, and those structures simply shrug and hold on. It's a bit like drawing a tiny circle with glue on a balloon before you blow it up. As the balloon expands, the circle might hardly change at all, because the glue holds that patch of rubber together. Galaxies, solar systems, atoms, they're glued by gravity and electromagnetism, resisting the large-scale stretch. The expansion of the universe cares mostly about the big, empty spaces in between. You drift closer to one of these bound systems, a star with a planet, warm and calm. You see the planet trace its orbit, again and again, year after year. The gentle tug of the star's gravity keeps it in place, like a stone in a sling. Expansion doesn't peel the planet away. The gravitational pull inside this little system overwhelms the very slight tendency of space to stretch. If expansion were a breeze, gravity here is a sturdy rope tied to a tree. Now you zoom out again, back to the grid. The language that physicists use for this is curved spacetime. Mass and energy tell spacetime how to curve, and that curvature tells matter how to move. On large scales, where matter is distributed fairly evenly, the overall solution to Einstein's equations looks like a universe that can expand or contract. The expansion is not a force pushing on things. It's a feature of the geometry itself. You imagine walking on a gently moving walkway in an airport. If you stand still, the walkway carries you along. If you walk against it, you can stay in place relative to the building. On cosmic scales, galaxies that are far apart mostly stand still in their local space, and the expansion walkway carries them away from each other. On small scales, gravity and other forces are like you, walking the opposite way, cancelling out the motion of the belt. You notice something soothing in that idea. Expansion is not an attack on structure. It's the background rhythm. Local relationships, atoms in your body, you held by Earth, Earth held by the sun, are stronger, more intimate. They form islands of stability in a sea of gentle drift. It's as if the universe is saying, I may stretch over all, but I also allow pockets where things hold together, where stories can form, where you can exist. In your mind's eye, you now shrink much, much smaller, down to the scale of an atom. It's like entering a quiet cathedral of probability clouds. The electron isn't a little planet racing around. It's a fuzzy presence, a smudge in space where it's likely to be found. The electromagnetic attraction between that electron and the nucleus is immense compared to the feeble effect of cosmic expansion on such a tiny region. The fabric may stretch on megaparsec scales, but here, inside this atom, it might as well be perfectly still. You drift outward through layers, atoms to molecules, molecules to cells, cells to organs, organs to you. At each step, forces bind things, chemical bonds, cellular structures, tissues woven together. None of these feel the stretching of the universe. They are like tiny knots in a vast rope. The rope can lengthen in some distant portion without untying the knots where you are. The same is true for a galaxy. You picture the Milky Way now, its spiral arms smudged with starlight and dust. Gravity has pulled hundreds of billions of stars into this whirlpool over billions of years. Inside the galaxy, stars orbit the center, bound in a gravitational dance. The expansion of space between galaxies doesn't simply pry these stars apart, because the galaxy's own gravity is stronger on these scales. The Milky Way, in effect, has opted out of the expansion. It sails through expanding space as a cohesive ship, not as a cloud of unconnected debris. Still, that expansion is there, quietly, beyond the edges. Between galaxy clusters, in the wide, thin cosmic voids, the grid lines of space-time keep stretching. If you could somehow paint a gigantic cube of empty space, 100 million light-years on a side, and then check on it billions of years later, the distances inside that cube would have increased. The cube would be larger not because its edges moved through anything, but because the fabric inside it grew. You sigh, a small breath in the dark. Maybe this is the calmest way to think of it. The universe is not throwing things away from each other. It's giving them more room. On large scales, everything gets more spacious. On small scales, the bonds we know gravity in a galaxy, the pull of Earth under your back right now, the forces inside your own cells keep their shape. If you listen to your own body for a moment, you feel your weight on the bed, the pressure of gravity holding you close to your planet. You feel your heartbeat, anchored by the regular firing of cells, ions moving across membranes. None of that depends on the size of the visible universe. As far as your atoms are concerned, cosmic expansion is practically non-existent. There's a kind of kindness in that separation. The grand, slow changes of the cosmos do not yank away your immediate world. They set the stage, define the overall lighting and backdrop, while allowing your local scene to play out undisturbed. You can fall asleep safely in a universe whose fabric stretches, knowing that the bonds that matter most to your experience are strong enough to ignore that distant swell. And yet, as you close your eyes a little more, you might feel a quiet kinship with that expanding fabric. You are made of particles born in that same space-time, forged in stars whose light has ridden the stretch of the universe. On one level, you are an island of resistance to expansion. On another, you're a tiny pattern in the very cloth that's growing. Both can be true. Maybe the universe doesn't just love repeating patterns. Maybe it loves balance between motion and structure, between vast, stretching emptiness and the small, dense places where consciousness can bloom. Ask questions, and then, finally, rest. You're still floating above that silver grid of space-time in your mind, watching it breathe outward. Now a softer, more technical curiosity drifts in. If the universe is expanding, how fast? Is it a gentle stroll, a jog, or a sprint? You picture a slope on a quiet graph, the Hubble slope. On the horizontal axis, distance. On the vertical axis, recessional speed. Each galaxy is a dot. Draw a line through all those dots, and the steepness of that line is the Hubble constant, the number that tells you how many kilometers per second of speed you get for every megaparsec of distance. 1 megaparsec is about 26 million light-years, so each tick step along that axis stretches the imagination as much as the math. You imagine lying on your back at the base of that graph, the line rising above you like a gently tilted ramp into space. Somewhere along the ramp is the current best estimate of the expansion rate, dozens of kilometers per second for every megaparsec. Not a cosmic explosion roaring in your ears, more like a slow, relentless drift that only shows itself across vast distances. To understand how we measure that slope, you're carried down into the toolbox astronomers use, the cosmic distance ladder. You see it as an actual ladder now, wooden rungs glowing faintly in the dark. The lowest rungs are nearby distances measured with geometry, like stretching a tape measure across the sky. For close stars, astronomers use parallax, watching how a star appears to shift slightly against distant background stars as Earth orbits the Sun, the way your finger seems to jump left and right if you close one eye and then the other. You float beside a star being measured this way, feeling the vast triangle formed by Earth at 2 points in its orbit and the star at the tip. The angle is tiny, a whisper of a tilt, but with careful instruments and patient observations, the distance can be teased out. You feel the satisfaction of getting that first rung of the ladder right. Higher up, another rung appears. Cepheid variable stars. In your mind, they're like cosmic lighthouses that pulse in a steady rhythm. Bright, dim, bright, dim. Early in the 20th century, Henrietta Leavitt discovered that the period of their pulsing is related to their true brightness. Slower, longer pulses mean intrinsically brighter stars. So, if you measure how fast they pulse and how bright they look from Earth, you can infer how far away they actually are. They become standard candles, objects whose true luminosity, flickering metronomes scattered through the galaxies. You watch one Cepheid beating slowly in some distant galaxy, its golden light rising and falling like a heartbeat in the dark. Astronomers catch that rhythm, compare it to the brightness they see, and climb another rung. Now they can measure distances to galaxies far beyond what pure geometry could reach. Farther up the ladder, another kind of candle glows. Type Ia supernovae. In your mind's eye, they are brief, breathtaking flares, the explosive deaths of white dwarf stars that reach a critical mass and ignite in a runaway thermonuclear flash. Because the physics of these explosions are remarkably similar, their peak brightness is also fairly standard. That makes them powerful beacons visible across immense distances. By measuring how bright a Type Ia supernova appears, you can estimate how far away its host galaxy is. Now the ladder reaches deep into the Hubble flow realm, where cosmic expansion dominates. Rx +1. You hover above this whole structure parallax at the base, Cepheids in the middle, supernovae higher up, and you see how they connect. Nearby Cepheids calibrated by parallax, distant Cepheids and supernovae calibrated in turn. Step by careful step, the distances stretch outward, and with them, the dots on that graph of speed versus distance line up. From this late-time view of the universe, the slope of the line, the Hubble constant, lands around the low 70 seconds in kilometers per second per megaparsec. Then, gently, you're pulled even farther back, beyond individual galaxies and supernovae, to something older and more primal. The cosmic microwave background, the afterglow of the Big Bang, spread across the whole sky as a faint, almost uniform bath of microwaves, the cooled remnant of a time when the universe was hot and dense. Satellites like Planck have mapped tiny temperature variations in this afterglow with exquisite precision. Those variations encode information about the contents and geometry of the universe, and when cosmologists fit their models to that pattern, they can infer what the expansion rate should be today. From this early time perspective, the Hubble constant comes out lower, around 67 or so. You picture two hills now, seen from different sides. From one direction, they look steeper, from the other, shallower, but it's the same hill. That mismatch between the late-time distance ladder measurements and the early-time cosmic microwave background inferences is called the Hubble tension. It's like listening to two clocks ticking in a quiet room and realizing they're almost but not quite keeping the same time. You float in that room now. One clock is labeled Local Universe, built from Cepheids, supernovae, and other nearby distance measures. The other is labeled Early Universe, built from primordial light and large-scale structure. They disagree by just a few kilometers per second per megaparsec, only a handful of units, but the precision of modern cosmology makes that difference feel loud. Papers are written, conferences held, new models considered. Maybe there's some subtle systematic error in the ladder. Maybe the early universe physics needs an extra ingredient, like early dark energy or a new kind of particle. Recently, you see new rungs being added to the ladder. Mirror variables, gravitational wave standard sirens, and other clever methods to cross-check both sides of the tension. Their results glimmer in the dark like additional lanterns, some leaning toward one value, some toward the other, all nudging cosmologists to look harder. And in your mind, because this is a bedtime universe, the debate doesn't feel stressful. It feels like a gentle puzzle laid out on a quiet table. On one piece of the puzzle, the Planck satellite's precise ripples in the cosmic microwave background. On another, decades of painstaking measurements of stars and supernovae in the nearby cosmos. The edges match beautifully. It's just the middle that seems to bulge a little. You breathe in slowly. Maybe the universe is hinting that our picture is almost right, but not quite complete. Maybe dark energy isn't perfectly constant. Maybe something subtle happened in the first few minutes after the Big Bang that leaves a faint fingerprint in today's expansion rate. Or maybe, just as often happens in science, there are still small biases in our measurements waiting to be uncovered. Either way, the Hubble constant becomes more than a number. It's a story about how we take light, stretching across billions of years, and turn it into a ruler. How we build ladders into the dark using stars that pulse and stars that explode. How we compare the baby picture of the universe to the adult it has become, and try to see if the two really match. As you relax deeper into your pillow, you might imagine yourself holding that sloping line in your hands, feeling its tilt between your palms. Whether it leans a little steeper or shallower, the basic truth remains. On the grandest scales, galaxies recede, Space grows, and the same laws that govern atoms in your body let us measure the speed of the universe itself. And maybe, just maybe, the fact that we're still arguing about a few kilometers per second is its own kind of wonder, a sign that we've come far enough to notice such a delicate discrepancy at all. You're deeper into the night now, held comfortably by gravity, by your bed, by all the small forces that keep you together. Out beyond your walls, galaxies still drift on that stretching fabric. And now, like a soft whisper at the edge of hearing, another question arrives. What is pushing the universe to expand faster and faster? You imagine the cosmic grid again, those pale silver lines marking space. For a long time, in your mind's story, the grid just stretched steadily, slowing a little as gravity tried to pull everything back together. That was the old expectation. Expansion should decelerate, like a tossed ball climbing upward, slowing under Earth's pull. But then you watch the story reach the late 1990 seconds. In your imagination, you float over two teams of astronomers, scattered across mountaintop observatories and chilly control rooms. They're tracking Type Ia supernovae, those bright, standard candle explosions you've already met. Each one is a flare in the dark, a way to measure how far a galaxy is and how the expansion has behaved over cosmic time. You glide closer to one such supernova, blooming like a brief white rose against the black. Its light pours through the universe, its brightness and redshift imprinted with information. When researchers collect many of these flares nearby and far away, and plot how bright they appear for their redshift, they expect to see the signature of a slowing universe. But as you hover over their graphs, you notice something odd. The distant supernovae are just a bit dimmer than they should be if expansion had always been slowing. Dimmer means farther away than expected. Farther away means the universe must have expanded more than anticipated in the time that light was traveling. Instead of a ball slowing down, it's as if the ball, halfway up, suddenly felt a mysterious shove and started speeding up. Cosmic acceleration. You see the scientists staring at their data in a mixture of disbelief and quiet excitement. They check their instruments, their calibrations, their assumptions. But the pattern holds. The universe's expansion is not just continuing, it's accelerating. Something, some form of energy, seems to be built into space itself, acting like a gentle anti-gravity on large scales. You picture this dark energy not as a substance swirling in clouds, but as a property of empty space. Every cubic meter of vacuum, even the quiet one around your hand right now, has a tiny amount of energy associated with it. Not enough to tug at atoms or chairs or planets, but when you add it up over the vast reaches between galaxies, its effect dominates. In your mind, you float in one of those vast voids, far from any galaxy. It's cold here, quiet and almost perfectly empty. You stretch out your hand and feel nothing, and yet, conceptually, there is this faint, uniform pressure, a tendency for space to expand. You can't hear it, you can't touch it. But mathematically, it sits in the equations of general relativity, like a small, persistent term that never goes away. Physicists often model dark energy as a cosmological constant, a fixed energy density of the vacuum that stays the same as the universe expands. If that's true, then as space grows, the total amount of dark energy grows too, because there's more space filled with the same energy density. Gravity from matter gets diluted as the universe expands, but dark energy does not thin out. It keeps its strength, and eventually it takes over the dynamics of expansion. You visualize a cosmic tug-of-war. On one side, clumped matter and dark matter pull inward with gravity, trying to slow expansion and make structures. On the other, dark energy pushes outward in a subtle, uniform way, not pulling on galaxies directly, but curving space-time so that the overall solution is accelerated expansion. In the early universe, matter's gravity was stronger. Structures formed, stars ignited, galaxies assembled. Over billions of years, as matter spread thinner, dark energy's relative influence grew, until, a few billion years ago, it began to dominate. From your vantage point outside time, you watch a graph of the universe's expansion rate rise and fall. At first, soon after the Big Bang, expansion is incredibly fast. Then it slows as gravity fights back. Then, in the more recent cosmic era, the curve's slope changes sign and begins to bend upward acceleration. You can almost feel that inflection point, like a soft click in the rhythm of the cosmos. What exactly is dark energy, though? That question floats beside you like a lantern with no label. Some physicists think it really is just the cosmological constant, a fixed vacuum energy. Others consider the possibility of a slowly changing field, sometimes called quintessence, whose energy density evolves over time. In those scenarios, dark energy might have been weaker or stronger in the past, and its future behavior could decide the ultimate fate of the universe. For now, observations from supernovae, from the cosmic microwave background, and from the way galaxies cluster all point to a picture where dark energy makes up roughly 70% of the total energy content of the cosmos. Ordinary matter stars, gas, your body accounts for less than 5%. Dark matter holds another roughly 25%, shaping galaxies with its invisible gravity. The rest, this quiet driver, dark energy, setting the pace of expansion from behind the scenes. You let that sink in for a moment. Most of the universe, by energy content, is in a form we don't fully understand. And yet, rather than panic, you might feel a strange peace in that ignorance. The sky you see still looks the same. The laws we do know still work reliably enough to build bridges, launch spacecraft, and keep your phone glowing beside your bed. Maybe the universe is allowed to keep some secrets, even while it lets us measure their effects. You listen to your breathing, slow and steady, and imagine each exhale as the universe stretching just a little more. Not because of you, of course, but as a metaphor, a gentle outward motion, powered by something fundamental and unseen. The galaxies are like lanterns hung in a dark hall, and dark energy is the quiet hand dimming the lights and widening the distance between them, not with violence, but with a subtle, persistent pressure. Sometimes, late at night, cosmologists wonder whether dark energy will stay constant forever or change. Will it remain a soft, steady push, leading to a universe that expands forever, growing colder and emptier, stars aging and dying in a slowly thinning sea? Or will it strengthen, eventually tearing apart even-bound structures in a more dramatic Big Rip? These are questions we'll wander through later, but they all begin with this mysterious, gentle actor, the driver of acceleration. For now, you don't need the exact equations. You just need the feel of it. Space itself has an energy, and that energy bends the storyline of the cosmos toward faster expansion. Dark energy is like a faint background hum in a piece of music. You might not notice it on first listening, but once someone points it out, you can't unhear it. It shapes the mood of the whole song. As sleep draws a little closer, you might think, maybe the universe, like a good storyteller, leaves some characters partly in shadow. We don't need to see everything clearly to be part of the tale. We ride on a small world, in a dusty spiral arm of a galaxy, embedded in a vast web of matter, all of it surfing on a sea of dark energy. You are here, on this one night, feeling your heartbeat while the expansion of the universe gently accelerates far beyond your walls. And somehow, that enormous mismatch of scales you're breathing, that cosmic speeding up fits together in the same physics. Maybe the universe just loves that kind of contrast. You're drifting now, in a darkness that feels almost comfortable, like a thick blanket around the cosmos. We've talked about stretching space and the quiet shove of dark energy, and now you're ready for a softer question. What, exactly, is the universe made of? You imagine the whole cosmos as a single, simple pie sitting on a table in front of you. You can't eat it, unfortunately, but you can slice it in your mind. The first slice you reach for is the obvious one, the stuff you know. Stars, planets, gas, dust, the atoms in your body. You expect it to be most of the pie, but as the knife moves, something surprising happens. That familiar slice is tiny, just a slim piece, only a few percent of the whole. Roughly 5% of the universe, give or take, is made of ordinary matter, the protons and neutrons and electrons that build everything you've ever touched. You hold that slim slice up in your imagination and see it shimmering. All the galaxies, all the glowing stars, your pillow, your bones, the air in your lungs, everything you call stuff is crammed into that thin wedge of the cosmic pie. It feels a little humbling, like finding out your entire life so far has taken place in just one small room of a much larger house. The next slice is darker, literally. About a quarter of the pie, around 25 to 30%, is dark matter. It doesn't shine, doesn't interact with light, doesn't glow in any telescope, but it tugs on galaxies with its gravity. Without it, spiral galaxies would fly apart as they spin. Clusters of galaxies wouldn't hold together. The large-scale web of cosmic structure would look completely different. You picture this slice as a matte black wedge, heavy and silent, cradling the glittering slice of ordinary matter like a hidden hand. In your mind, you turn that dark slice over. You can't see it, but you can see what it does. Galaxy rotation curves that stay flat instead of dropping off. Gravitational lensing, where invisible mass bends the path of light from background galaxies, like a glass lens in space. Subtle patterns in the cosmic microwave background. Little ripples that tell us how much gravitating stuff was present in the early universe. All hints, all fingerprints, pressed into the sky. And then there's the largest slice by far, the one that seemed almost rude when it first appeared in the data. Dark energy. Roughly 68% of the total cosmic energy budget, if you trust the blend of measurements from the cosmic microwave background, supernovae, and galaxy clustering. In your mental pie, this slice looks strangely empty, almost transparent, but it takes up more than half the circle. This is the quiet pressure that drives acceleration, the energy of space itself. You slide the pie chart closer, hovering above it like a small planet. 5% ordinary matter, about 27% dark matter, about 68% dark energy. Photons and neutrinos, light and ghostly particles, barely make a sliver at the edge, thin as a line of frosting. The numbers wobble slightly depending on which measurements you use, but the general recipe is the same. The universe is mostly dark, in both senses, unseen and mysterious. You might feel a little left out, discovering that your atoms are such a small fraction of reality. But as you float, another thought arrives. That 5% is exactly the kind of matter that can make chemistry, and planets, and stars, and you. It's like a tiny patch of fertile soil in a wilderness of rock, small but incredibly rich. Maybe the universe doesn't need a big fraction of ordinary matter to do something remarkable with it. Now you zoom out from the pie and drift toward the evidence that pins these numbers down. One piece comes from the cosmic microwave background, the faint afterglow of the Big Bang. When missions like Planck mapped small temperature variations in that ancient light, they produced a pattern of hot and cold spots across the sky. Hidden in that pattern are acoustic peaks, like the frozen echoes of sound waves ringing through the early plasma. Their heights and spacing depend sensitively on how much ordinary matter and dark matter existed back then, and on the geometry of space. By fitting models to those peaks, cosmologists can infer precise values for the matter density and dark energy fraction. You imagine those peaks as a quiet cosmic music score, etched into the sky. Each note's volume tells you something about how matter and energy were balanced when the universe was just 380,000 years old. Reading that score, scientists learn that the total matter fraction is about 31%, and that to make the expansion history fit, the remaining roughly 69% needs to be dark energy, a recipe pulled out of whispers in ancient light. Another piece of evidence comes from how galaxies cluster today. In your mind, you return to that sponge-like map of the universe, the filaments, the walls, the yawning voids. The size of certain features in this cosmic web, like the characteristic scale of baryon acoustic oscillations, fossil sound waves frozen into the matter distribution, depends on the same underlying ingredients. Measuring those structures is like tasting the cake after it has cooled, checking that it matches the recipe inferred from the batter. So far, it does, within uncertainties. And then there are more recent, delicate measurements that hunt specifically for the missing bits of the ordinary slice. For years, cosmologists knew how many baryons, protons, and neutrons the early universe should contain, from calculations involving nuclear reactions right after the Big Bang. But when they counted baryons in stars and gas, about half seemed to be missing. Only recently have observations using fast radio bursts, sharp radio pulses from distant space, traced much of that missing matter, spread as thin, hot plasma through intergalactic space. The universe's ordinary slice is finally accounted for, even if most of it floats between galaxies, unseen. In your inner vision, this is beautiful. The visible slice of the pie isn't just in bright stars and galaxies, but in faint threads of plasma bridging the dark. Like mist between forest trees, most of the ordinary matter lives out there, quiet and diffuse, carrying the majority of the slice you belong to. You let the pie fade and instead imagine three colored streams flowing through the universe. One is warm and golden, ordinary matter, the stuff of clouds and rocks and oceans. One is deep blue-black, dark matter, invisible, yet shaping motion and form. One is pale and almost colorless, dark energy, the smooth background that decides how fast space stretches. These three streams interweave across billions of years, their relative strengths changing the tempo of cosmic history. There's a gentle thought hiding in all of this. You are made of the smallest slice, living on a small world, looking out at a universe that is mostly made of things you cannot see. And yet, using the light that does reach you, and the equations that describe how space-time bends and how atoms behave, you can reconstruct that invisible recipe to remarkable precision. As you feel your eyelids grow heavier, you might think of yourself as a tiny experiment happening inside that 5% slice. Dark matter holds your galaxy together, dark energy guides the overarching expansion, and ordinary matter, under those conditions, has a chance to form complex, fragile structures like you. The pie is mostly dark, yes, but the little bright piece seems to be just enough for questions, and wonder, and long, slow nights, like this one. Maybe the universe's recipe is not an accident you have to solve before you sleep. Maybe it's more like a lullaby. Three repeating notes: ordinary matter, dark energy, playing quietly beneath every star you've ever seen. You're resting deeper now, breathing slow, while the universe above you keeps doing its strange, patient thing, expanding, cooling, rearranging itself over billions of years. At some point, the obvious question quietly appears beside you like a friend sitting down on the edge of the bed. If it keeps changing, where is it all going? You imagine time as a long, dark corridor stretching away from you. The present moment is a small, lit doorway. Behind you lies everything that has already happened. The Big Bang, the forging of atoms, the birth of stars and galaxies, the formation of Earth, the quiet rhythm of your own life. Ahead, the corridor curves gently out of sight. Somewhere along that curve, the universe has chosen an ending, or at least a direction to drift toward. You begin by floating forward just a little way, not to the very end, but far enough that stars have mostly burned through their fuel. In this future, the expansion continues and keeps accelerating, powered by dark energy that behaves like a cosmological constant, a steady, unchanging pressure woven into space itself. Galaxies slide farther apart, the night sky thins, its constellations pulled slowly out of shape. In your mind's eye, the universe is a long, slow exhale. Stars age and die. New stars form more rarely, because the gas that once cooled and pooled into bright newborn suns is used up or locked away. Over unimaginable timescales, only faint red embers remain cool, dim stars glowing like coals at the end of a fire. Eventually, even they go dark. This is the path to heat death, or the big freeze. It sounds dramatic, but it's really a story of things running down. Entropy increases. Energy spreads out more evenly. Temperature differences fade. Without temperature differences, nothing can do useful work. No engines, no metabolism, no weather, no life. The universe settles into near uniformity, still expanding, still cold, with particles and light thinned out across an ever-growing volume. You picture this distant era as a vast, deep blue fog. There are no sharp points of light here, just almost empty space with a sprinkling of low-energy photons and the occasional, lonely particle. Black holes dominate for a while, swallowing matter and then, over stupendous durations, evaporating slowly via Hawking radiation. When even the black holes are gone, only a dilute sea of radiation and the lightest particles remains. The universe is like a song stretched out so far in time that the notes become a continuous, fading hum. The idea can feel bleak, but there's another way to hold it, as the natural outcome of a cosmos that started in a low-entropy, highly structured state. Everything complex that has ever existed, including you, rides the temporary wave between that ordered beginning and that smoothed-out end. You are part of the universe's brief period of intricate structure, like frost patterns blooming on a window before the glass warms and the shapes melt away. You drift a bit further down the corridor and let the story shift. What if dark energy isn't perfectly constant? What if, instead of staying steady, it slowly grows stronger over time? Not just enough to keep expansion accelerating, but enough to push harder and harder, like a tide that keeps rising past every marker. In that scenario, the acceleration becomes so intense that it doesn't just separate galaxy clusters. It eventually overpowers the gravitational glue that holds galaxies together. You picture the Milky Way stretching, its spiral arms pulled apart like taffy. Later, the same fate befalls solar systems. The space between stars, then between planets and their suns, grows faster than gravity can compensate. You hover near a quiet planet in this imagined future, feeling the subtle tug of its star. Then you sense something stronger. The background expansion, now ferocious on these smaller scales, beginning to prise the orbit open. Planets drift away. Stars themselves, once held together by their own gravity, begin to feel the strain. The nuclear furnaces at their cores sputter as their matter is torn outward. If the dark energy's equation of state dips below a certain threshold, if its pressure is sufficiently negative, in what physicists call phantom energy, the acceleration can, in some models, become infinite in a finite time. This is the big rip. In the approach to that final moment, even atoms would be unbound. Nuclei pulled apart, then nucleons, then the very building blocks beneath them. Structures fail in a cascading hierarchy. Galaxy clusters, galaxies, star systems, planets, molecules, atoms, all undone by the runaway expansion of space. You might shiver slightly at that thought, so you zoom back to a safer mental distance. This is only one possible ending, one that depends on dark energy acting in a very particular way that current observations don't demand but also don't entirely rule out. For now, phantom energy is a speculative character in the story, not a confirmed one. Still, imagining it helps you understand how sensitive the universe's fate is to the properties of this mysterious component. You let the scene dim and try on yet another future. What if dark energy fades over time instead of staying constant or growing? Perhaps it behaves like a field that slowly relaxes, its influence weakening as the universe expands. In that case, gravity from matter and dark matter could one day reclaim dominance. The expansion might slow, stop, and then reverse. You picture the cosmic grid again, its lines first stretching, then pausing, then ever so gently beginning to contract. Distant galaxies that once receded start to approach. The long exhale becomes an inhale. Over even longer timescales, structures merge, and the universe grows denser and hotter again. This is the path to a big crunch, a reversal of the Big Bang's expansion, ending in a hot, dense state where space itself shrinks to extreme conditions. Some models go further and suggest that a crunch might not be a true end, but a bounce leading to a new cycle of expansion, perhaps with new physical conditions. In those cyclical universes, the corridor of time doesn't end in a wall. It loops. The cosmos breathes in and out, across epochs so vast that any particular civilization, any particular star, is a mayfly's blink in comparison. From your perspective on a soft mattress, each of these futures heat death. Big rip, big crunch, cyclic rebirth feels impossibly distant and abstract. They are questions for equations and telescopes and patient surveys, for instruments that measure the subtle way galaxies cluster or how the light from the early universe ripples across the sky. They depend most sensitively on the behavior of dark energy, summarized in a simple parameter that encodes how its pressure relates to its density. But behind that simple parameter lies an entire unknown physics we have yet to uncover. You inhale gently. Maybe the universe has already chosen one of these futures. Maybe there are possibilities we haven't thought of. New observations hint that dark energy might not be perfectly constant, that its influence could evolve over time, opening doors to scenarios where expansion slows, or even reverses, or races ahead more wildly than we expect. Each new dataset is like a flashlight beam briefly cutting across that far end of the corridor, illuminating a slightly different outline of what might be waiting there. For you, here, tonight, perhaps the most comforting thought is this. All of these endings are so far beyond human timescales that they barely register compared to the life of a star, let alone the life of a person. The sun will live and die, the Milky Way may collide and merge, species will rise and fall, all long before the universe commits to a final act. You feel the weight of your body, the warmth of your own tiny patch of ordered matter. Whatever the ultimate fate, slow fade, sudden tear, grand collapse, or endless cycle, you belong to the brief, luminous middle of the story, where galaxies blaze and chemistry dances, And questions like this can even be asked. Maybe the universe just loves to keep its final page unwritten, even while it leaves enough clues for us to trace the outline and to fall asleep wondering which ending it prefers. You're very far down the corridor of time now, at least in your imagination. Behind you lie bright galaxies, crowded starfields, nebulae glowing pink and blue. Ahead, the light starts to thin, the colors drain away. You're about to walk into the universe's longest, quietest evening, the path toward heat death. You start in a familiar era, just a bit beyond our own. Galaxies are still recognizable here. Spirals, ellipticals, clusters of them, binding together with invisible threads of dark matter. Stars burn like lanterns on a small rocky world in a minor galaxy. Creatures like you once looked up and wondered about it all. You can almost feel the leftover warmth on that long-vanished planet, like heat lingering in a bed after someone gets up. Then you drift forward. Billions of years pass like slow breaths. Star formation begins to wind down. The gas clouds that fuel new stars are used up or locked into dead remnants. The big, hot, blue stars burn out first dramatic but short-lived, like fireworks on a summer night. Smaller, redder stars keep going, burning their fuel more carefully, like people who sip tea instead of gulping it. You float near one of those long-lived red dwarfs. Its light a soft ember in the dark. Planets still circle it, maybe with frozen oceans and silent continents. The star's glow feels warm on your imaginary skin, but you know the clock is ticking. Given enough time, trillions of years, these stars too exhaust their fuel. Their cores cool, and they fade into faint, dense embers, white dwarfs sliding toward blackness. Every time a star dies, the universe changes a little. The easy energy is gone. Thermodynamics tells you that energy tends to spread out, to move from concentrated hot places to diffuse, cool ones. That spreading is what we call entropy, increasing. Right now, in your world, that gradient hot sun, cool space lets life exist. It drives weather, fuels ecosystems, powers engines. But in the far future, the gradients flatten. Temperature differences shrink. The cosmos evens out. You drift farther. Galaxies themselves begin to transform. Repeated mergers shuffle their shapes. Spirals collide, turning into large, featureless ellipticals. There are fewer bright gas clouds, fewer newborn star clusters. The night sky, for any observer who might exist, looks sparser, with fewer young blue stars, more faint, red remnants, like a city where most of the windows are dark, and only a few tired lamps burn in the distance. Eventually, even those lights go out. The universe moves into the degenerate era, a time when almost all normal matter is locked into white dwarfs, neutron stars, black holes, and a spread of cold planets and rocks. You glide past a lonely planet, a barren, frozen sphere circling a dead ember. The surface is incredibly cold. Your breath would freeze in midair if you could breathe here at all. Above, the sky is not black. Exactly, there's a faint mist of starlight and background glow, but it feels emptier than anything you've ever imagined. Still, gravity keeps working. Over unimaginable spans of time, chance encounters and slow orbital shuffles fling planets out of star systems, stars out of galaxies. Some remnants fall into black holes, others wander into galactic space, dark stones drifting through a thinning sea of radiation. You picture them as tiny, frozen seeds blowing across an endless cold field. Black holes grow fat for a while, swallowing whatever strays too close. They become the main actors in this late cosmic drama. At the center of what used to be galaxies, supermassive black holes wait, invisible except for the slow trickle of matter that still falls in. But even they are not eternal. Quantum effects near their event horizons cause them to emit Hawking radiation, losing mass bit by bit, like ice cubes evaporating on a table over trillions and trillions of years. You zoom forward to watch one of these giants fade. At first, it hardly seems to change. Then, after an absurd amount of time, far longer than the current age of the universe, it has shrunk. As it becomes smaller, it radiates more strongly, heating up as it dies. In a final, brief flash, it evaporates completely, releasing its remaining energy as a burst of particles and radiation into an already thin, cold cosmos. Once the black holes are gone, the universe enters what some cosmologists call the dark era. No stars, no bright galaxies, no new sources of organized energy, just a diffuse soup of elementary particles, low-energy photons, maybe incredibly long-lived relics like protons if they don't decay, though some theories suggest that even protons eventually fall apart. The cosmic temperature creeps ever closer to absolute zero, never fully reaching it, but getting so near that the difference hardly matters. You can imagine this state as a vast, dim ocean of almost uniform temperature. There are no free energy gradients left to drive complex processes. In such a universe, nothing much happens. No new stars ignite. No large-scale structures form. It's not an explosive ending. It's a slow fading. The cosmos doesn't slam the door, it lets the light fall, photon by photon, until all that remains is a gentle drizzle of low-energy radiation. Lying in your bed, you might feel a tiny ache at this picture. Everything that ever was, galaxies, planets, trees, cities, friendships, compressed into a fleeting period before the great, quiet leveling. But then another thought arrives, softer. The only reason you can even imagine this future is that the universe began in a low-entropy state, unusually ordered, with room for complexity to grow before the flattening out. You are part of the ripple between those two extremes, the hot, dense beginning and the cold, diffuse ending. On human timescales, the universe feels almost static. Stars rise and set. Seasons come and go. Galaxies change only in the silent language of long exposures. But on cosmic timescales, you are living in a remarkably active, luminous moment, a kind of cosmic afternoon before the long evening sets in. You picture a fireplace that will one day burn out. Right now, it's crackling, bright orange flames, shifting shadows, warmth across your hands. Later, it will be only embers. Much later, cold ash. Heat death is that final stage. But the value of the fire isn't lessened by the knowledge that it ends. If anything, its warmth is more precious because it's temporary. So as you listen to your own breath, feel the faint warmth of your body against the air. You can think of yourself as a tiny fluctuation in the universe's long journey toward equilibrium, a small, local rebellion against entropy, powered by the gradients that still exist. Life is what happens while the universe is allowed to be uneven. One day, far beyond any night you will ever know, the cosmos may reach that near featureless state. No stars to wish on, no galaxies to map, only a vast, quiet field of almost nothing. But the fact that this might be its destination makes your current moment, in a bright, cluttered, noisy universe, feel like a rare and beautiful stop along the way. Maybe the universe, in its long, cold evening, will remember nothing. But right now, you remember, you imagine, you wonder, and then you rest. You're drifting in that long, dim future again. But this time the air in your imagination feels a little tighter, a little stranger. We've walked through the quiet fade of heat death, a universe thinning and cooling into stillness. Now you open a different door, one with a sharper edge, a future where space itself turns on the things it once gently carried. You begin, as always, lying where you are now. Your room feels solid. The bed holds you. The walls stand firm. Gravity keeps your body pressed softly into the mattress. Atoms in your bones hold tight hands, electrons humming in their quiet probability clouds. Nothing feels like it's being stretched, but in your mind, you let dark energy change character. Instead of a calm, constant pressure, you imagine it becoming stronger over time, a kind of energy with an equation of state that dips below a critical threshold cosmologists call W less than -1. They nickname it phantom energy. It sounds spooky, but you can think of it simply as vacuum energy with an extra push, one that grows more intense as the universe expands. You see the cosmic grid again, those silver lines marking space. In previous futures, the lines stretched steadily, their motion gentle, almost sleepy. Now, something changes. At first, the difference is subtle. The lines drift apart a little faster than before. But as time passes, that faster expansion feeds on itself. The more space there is, the more phantom energy it holds. The more phantom energy, the harder it drives, expansion. It becomes a runaway process, a cosmic feedback loop. You zoom out to watch galaxy clusters. They're like glowing cities, bound together by the gravity of dark matter and hot gas. For eons, they've resisted the universal stretch, their internal gravity stronger than the background expansion. But in this phantom-driven universe, there comes a day when the expansion becomes too aggressive even on these massive scales. You float between two clusters, feeling their mutual gravitational pull like a faint tug in opposite directions. Then you feel something louder beneath your feet, the metric of space itself, the mathematical distance between points, swelling faster and faster. One moment, the clusters seem stable. The next, the expansion's outward pull at these scales surpasses their ability to hold on. The cosmic web's filaments start to thin and snap. In slow motion, you watch a pair of clusters drift apart, their connecting bridge of galaxies stretching like caramel until it strands, then breaks. The once coherent superstructure of the universe, walls, filaments, nodes, begins dissolving. Not because gravity has weakened, but because the background expansion has become stronger than any bond stretching across those distances. You move closer now, into a single galaxy, our old friend, the Milky Way. Its spiral arms still curl in hazy arcs, but the outside universe is changing rapidly. Nearby clusters are already being torn from our local supercluster, receding at speeds approaching then surpassing what light can bridge. The observable horizon shrinks around the galaxy like a closing iris. Inside the Milky Way, for a while, things seem almost normal. Stars orbit the galactic center, dark matter forms its invisible halo, planets trace their paths. Gravity on these smaller scales is still stronger than the expansion for the moment, but phantom energy keeps intensifying. In the mathematics, there's a finite time in the future when the scale factor of the universe becomes infinite, and before that, there's a countdown. First clusters unbind, then galaxies, then star systems, then planets, then molecules, then atoms. You imagine a cosmic clock, its hands ticking down toward a time cosmologists sometimes call tripped. Text rip. Trip the moment of the big rip. Long before that final instant, the universe has already become a very strange place. You hover above a quiet solar system in this imagined future. A star shines faintly. Planets orbit as they always have. Yet, in the background, the accelerated expansion has grown so fierce that the star's gravitational hold on its outermost planets begins to slip. Orbits widen, deform, and eventually the gravitational binding energy, the glue that keeps the system together, is outmatched by the pull of the expanding metric. One by one, planets drift away, the system unspooling into space. Closer to the final moment, you watch the same thing happening at even smaller scales. Galaxies that once sat serenely in the cosmic web now feel their own stars being stripped. The expanding space between star and galaxy center acts like a tide that never turns. Like grains of sand lifted into a rising wind, stars are pulled from their orbits, flung into the widening void between what used to be stable structures. You move to an imaginary world in these last days. Maybe it has mountains, oceans frozen by earlier cosmic changes, or perhaps just bare rock. Standing there, if anyone could stand at all, the sky would not just be dark, it would be tearing. Galaxies and stars would streak toward the edges of visibility, as the scale of space between you and them changes faster than light can compensate. Constellations would distort wildly, then vanish. Then comes a more intimate betrayal. The same runaway expansion that broke clusters and galaxies begins to challenge planetary gravity. A planet's mass tries to hold itself together, but the metric expansion acting across its radius grows ever more violent. Eventually, the outward stretch across the planet's diameter exceeds the pull of its own gravity. The planet fractures. Crust, mantle, core ripped apart into smaller and smaller pieces. You shrink your focus again, down to a single human-sized object, your own body, lying in bed. If somehow you existed in such a universe at such a time, at some point in the countdown, the expansion would overtake the forces that keep Earth in orbit, then the forces that keep Earth intact, and finally the forces that bind you to yourself. Molecules, once held together by electromagnetic bonds, would be pulled apart as space stretches more quickly across their length than the bonds can respond. Approaching the final moments, even atoms are not safe. The electric attraction between electrons and nuclei is strong, but not infinite. In the Big Rip scenario, there comes a time when the stretching of space across the diameter of an atom exceeds that electromagnetic hold. Electrons are torn from nuclei, atoms dissolve into subatomic particles, and in the final, unimaginably brief fraction of a second before the singularity, Even nucleons, the protons and neutrons in the nucleus, may be unbound, the fundamental building blocks themselves scattered by the catastrophic surge of expansion. It sounds violent, like the universe ending in a scream rather than a sigh. But remember, this is one possible future, not a prediction etched in stone. It depends on dark energies, pressure being more negative than in a cosmological constant universe, and on that behavior persisting without change. Current observations are consistent with a constant dark energy. Phantom energy is still hypothetical, a mathematical path the universe might have taken, or could still be taking in a subtler way than we can yet see. You step back from the edge of that imagined singularity. For a moment, you let the noise hush. What remains is the feeling that the universe's fate is exquisitely sensitive to the nature of dark energy. A tiny difference in a parameter leading to dramatically different endings. A slightly different W in the equation separates an eternally cooling universe from one that ends in a finite, catastrophic tear. Lying there now, you're safely in a cosmos where, as far as we can tell, the data fit a more tranquil picture. Dark energy close to a cosmological constant, no obvious sign of phantom behavior. Still, you've walked this other road in your imagination, and it leaves you with a curious kind of gratitude. Maybe the universe doesn't intend anything, doesn't choose kindly or harshly, but from your vantage in this current epoch, it's hard not to feel thankful that space, so far, behaves like a patient host. Stretching, yes, but gently enough that galaxies, stars, planets, and people can come into being, hold together for a while, and tell stories about it. If some far-off measurement one day hints that we are, in fact, headed for something like a big rip, it will still be so far in the future that it will not touch your life, or your children's lives, or your species' lifetime. These scenarios play out across tens of billions of years. Against that enormity, your heartbeat tonight is a brief, luminous pulse, fragile, but also real, and entirely yours. So you let the phantom universe drift back into theory space, a cautionary tale written in equations. The room around you stays still, your atoms stay bound. The fabric of space, here and now, is quiet enough to cradle you while you close your eyes. Maybe the universe loves drama in its equations, but in this moment, it's offering you something much simpler. The chance to rest, knowing that, whatever the ultimate script, the tearing of galaxies is not your problem tonight. You're back in that long corridor of cosmic time, but now you turn your attention to a different door, one that doesn't open onto endless thinning and cooling, but onto a universe that one day decides to fall back in on itself. Tonight, you let yourself wander into the possibility of a big crunch, and maybe, just maybe, a cosmic rebirth. You start as you are now, lying still, held by Earth's gravity, with the faint hum of human life somewhere beyond your room. Out in space, the universe is expanding, galaxies gliding apart on that familiar stretching grid. But in your mind, you quietly adjust one ingredient. Dark energy no longer dominates forever. Perhaps it's weaker than we think, or it fades with time instead of staying constant. Maybe the total amount of matter and energy in the universe is just high enough, or the geometry curved just enough, that gravity ultimately wins. You picture the cosmic grid again, silver lines marking space. For billions of years, these lines drift farther apart. The universe passes through something like our current era. Stars burning, galaxies merging, structures growing in a restless dance. Then, ever so slowly, the rate of expansion begins to drop. At first, it's imperceptible, like the barely noticeable slowing of a thrown ball when it's still racing upward. You imagine yourself standing under a night sky deep in the far future. The constellations have shifted over unimaginable times. Galaxies merged, stars aged. If you could somehow watch the sky with impossibly precise instruments over eons, you'd notice a trend. Distant galaxies that once receded faster and faster are now receding more slowly. The graph of expansion versus time, which had been bending upward in acceleration, begins to straighten, then curve the other way. In your mind's eye, the universe's history looks like a great arch. On the left side, the Big Bang, a hot, dense beginning, the scale factor of the universe starting near zero. The arch rises as the universe expands. Somewhere near the top you sit tonight, in a cosmos still growing. On the far right, if gravity ultimately overcomes the expansion, the arch bends downward again. The scale factor stops increasing, pauses at a maximum, then begins to shrink. The expansion becomes contraction. You watch that turning point from a safe distance, like seeing a tide reach its highest mark on the sand before it begins to creep back. For a while, not much looks different. The universe is huge. Local structures, galaxies, clusters are still bound by their own gravity. But the large-scale flow changes direction. On the very biggest scales, average distances between unbound regions start to decrease instead of increase. Now you drift forward through that contracting phase. As the universe shrinks, matter grows more crowded on cosmic scales. Galaxies that once moved apart begin to move closer together. Collisions become more common. Clusters merge into even larger structures. Grand, glowing knots in the cosmic web. You float among them, watching arcs of hot gas light up in X-rays as structures slam together, like sparks in a great, slow-motion forge. The background temperature of the universe, which had cooled for billions of years, starts to creep upward. The diffuse radiation left over from the Big Bang, once stretched into cold microwaves, is compressed again. Its wavelength shortens, its energy rises, and the whole sky brightens in a faint glow. The cosmic microwave background, which had been a chilly 2.7 Kelvin, warms as space contracts, like embers glowing again when you cup them closer together. You move inward with everything else. In a steadily contracting universe, no region can remain isolated forever. Even galaxies that once drifted alone in vast voids are drawn into the general collapse. The density of matter increases. The large-scale curvature of space-time grows more extreme. You can almost feel space bending under the collective weight, like a flexible sheet sagging deeper as more marbles roll toward its center. Stars, too, are affected by this increasingly energetic environment. The growing density of matter and radiation changes how gas cools and collapses. There may be a late burst of star formation as fresh clouds are compressed, followed by a more chaotic era, where interactions are so frequent that stable systems are harder to maintain. In the final stages, as contraction accelerates, gravitational encounters become violent. Stars flung out of galaxies, others hurled inward, feeding central black holes. You zoom in on one of those black holes now, swollen by countless mergers, squatting at the center of a titanic conglomeration of matter. Its event horizon is a dark, perfectly silent circle. Around it, matter swirls in a bright disk, heating as it falls in, radiating fierce light. In a contracting universe, this kind of extreme environment becomes more common. Energy densities climb, temperatures rise, the cosmos grows hotter and more hostile to the kind of delicate chemistry that once made you. As you follow the collapse further, the entire universe begins to resemble its own very early stages. Dense, hot, tightly packed. The scale factor shrinks, bringing every region closer to every other. Eventually, if the contraction continues unchecked, space-time could reach conditions where our current theories break down. Densities and temperatures approaching or surpassing those of the Big Bang. You imagine this final phase as a kind of reverse firework. Instead of sparks flying outward from a central explosion, you see all the sparks, the galaxies, stars, planets, particles pulled inward toward a common fate. The night sky, if such a thing could still be perceived, grows brighter, then whiter, then too energetic for any eye or detector we know today. At the very end, in a classic Big Crunch picture, the universe collapses into an extremely hot, dense state. Perhaps a singularity, perhaps something just shy of it, where quantum gravity effects become crucial. It's like the cosmos returning to its own seed, compressing everything it has become back into an almost featureless, high-energy state. And here comes the gentlest speculative step. Some models suggest that this might not be a final end, but a bridge. Instead of a simple singularity, they imagine a bounce, where the contracting universe transitions into a new phase of expansion. On one side of the bounce, you have a big crunch. On the other, a new Big Bang. The laws of physics may transform or carry through in altered form, seeding a new cosmos with initial conditions molded by the previous one. You picture it as a heartbeat. The universe inhales, expansion, exhales, contraction, then inhales again, a new expansion. Across cycles so vast that each phase contains its own galaxies, its own chemistry, maybe its own attempts at life and curiosity. In some bouncing or cyclic models, entropy issues are addressed by mechanisms that dilute or reset disorder between cycles. In others, Each cycle is not identical but carries the memory of the last, the way tree rings carry subtle marks of the seasons they grew in. From where you lie, on your one small planet in one particular expansion phase, these ideas are less like predictions and more like stories physicists tell themselves while trying to connect general relativity with quantum mechanics. We don't yet know whether our universe is open, closed, or destined to bounce. Current observations suggest accelerated expansion that doesn't obviously point toward a big crunch, but the future behavior of dark energy is still not fully known. You breathe out slowly. There's something surprisingly comforting in the idea of a big crunch and cosmic rebirth, even if it remains speculative. It suggests that endings and beginnings might be more intertwined than they seem, that what looks like collapse on one scale could be preparation on another. Maybe you'll never know which path the universe actually takes. Maybe no single observer could ever span an entire cycle, if cycles exist at all. But the image lingers. A cosmos that doesn't just flare into being and fade, but pulses, like a chest rising and falling in sleep. You feel your own chest do the same. Inhale, exhale. For you, one breath ends and another begins, and there is a moment between them that is neither quite one nor the other. Perhaps, if the universe cycles, it too passes through such moments, brief, blazing instants of transition between vast eras of expansion and contraction. As your eyelids sink, you let both possibilities rest in your mind. A universe that stretches into a cold forever, and a universe that one day curls back into itself and starts again. You don't have to decide tonight which is true. You just have to feel the quiet wonder that you, made of borrowed stardust, are here in the middle of one chapter, dreaming about the last page and the first at the same time. You're drifting now toward the edges of things, the edges of what can be seen, known, reached, not the edge of the universe itself, because in our best models, there may not be a hard edge, but the edge of your possible view, even if you waited forever. Tonight, you float toward the idea of cosmic horizons, invisible boundaries that quietly rule what light can ever touch you. You start on your familiar small planet, lying as you are now, sky above you like a dark dome. To your naked eyes, the stars feel infinite. Through a telescope, the dome opens into depth, galaxies, clusters, faint smudges at the brink of visibility. It's easy to imagine that if you just had a better telescope, bigger mirror, sharper detector, you could see everything. But you can't. Not because of dust or clouds or technology, but because of time and the speed of light. Imagine yourself rising gently above Earth, high enough that the planet curves below you like a blue marble. You keep going, past satellites, past the orbit of the moon, past the outer planets and the far edge of the solar system. You travel purely in imagination, so you feel no acceleration, no nausea, just a soft upward glide. As you rise, you watch a glowing sphere forming around you, the observable universe. It's not centered on Earth as something special. It's centered on you, on this specific point in space-time where you're asking these questions. The sphere is defined by one rule. Any light that has had enough time since the Big Bang to reach you, traveling at light speed, lies within this bubble. Anything beyond that distance is, for now, beyond your possible sight. This boundary is called the particle horizon, the limit of what could ever have sent you light since the universe began. Beyond that horizon, there may be countless galaxies, perhaps arranged in similar webs and clusters, but their light simply hasn't had long enough to arrive. The universe could be finite or infinite out there. Your horizon doesn't care. It marks the limit of your conversation with the cosmos so far. You float at that horizon, imagining it not as a wall, but as a moving front in time. With each passing year, light from more distant regions has time to reach you, so the radius of the observable universe grows. New galaxies drift into view, not because they've crossed some physical border, but because their ancient light finally finishes the journey. In that sense, your horizon is always changing, like a fog line slowly retreating across a landscape at dawn. But then there is another kind of horizon, one that feels almost the opposite. If the universe's expansion is accelerating, driven by dark energy, there exists a distance beyond which light emitted now will never reach you, no matter how long you wait. Space between you and that light expands too quickly. This boundary is the cosmic event horizon. You picture it as a delicate shell, somewhere between you and infinity, defined not by the past but by the future. Inside it, light launched toward you will eventually arrive, given enough billions or trillions of years. Outside it, Light launched today is forever lost to you. The expansion will carry its source away faster than the light can close the gap. To feel this, you imagine two galaxies far from each other in an accelerating universe. They're like two boats on a river that's widening between them. If the current is gentle, one boat can still steer toward the other and eventually meet. If the current strengthens, there comes a point where no amount of rowing helps. The water between them is stretching too fast. The event horizon marks that threshold on cosmic scales. You hover just inside this horizon around your own galaxy. Over extraordinary future times, more and more distant galaxies will slip beyond it. Their last photons, already en route, will still arrive. But anything emitted afterward will never cross the gap. The visible sky shrinks, not in the sense that your local stars vanish, but in the sense that the deep tapestry of faraway galaxies slowly disappears, one by one, as they're carried beyond this invisible limit. There is a quiet, bittersweet feeling in that. Right now, with our telescopes, we can see light from galaxies whose present selves are already beyond our future reach. We are looking at their younger versions, preserved in photons that left long ago, even though their older selves are receding into a region of space that will never affect us again. The night sky is partly a fossil record of relationships already broken by acceleration. You drift out to the edge of what your descendants could ever see, if they had perfect instruments and infinite patience. The view is strange. Inside the horizon, a rich but finite set of galaxies, bound clusters, structures, outside and unseeable beyond. The universe may continue indefinitely, but any given observer's access to it becomes more limited with time. Horizons carve the infinite into a personal, finite bubble. Now you turn the picture around. Somewhere out there, on some distant world orbiting a distant star in another galaxy, a being, if one exists, might look up and trace their own observable bubble, their own particle and event horizons. Many of the galaxies they see, you will never see, and vice versa. Reality is larger than any one observer's sky. Each conscious mind lives inside a private dome carved by light and time. You let that thought sink in, then notice something strangely comforting. Within your horizon, within your share of the cosmos, the laws of physics appear uniform. The same atomic fingerprints, the same patterns in the cosmic microwave background, the same behavior of gravity. Even though you are cut off from most of the universe by horizons, the piece you can see seems to follow the same rules as any other piece. It's as if the universe is saying, you can't see everything, but what you can see is enough to understand the whole pattern. You might feel, as you lie there, a small echo of this idea in your own life. You will never see all times, all places, all histories. You live inside horizons of your own, cultural, emotional, personal. Yet, within your limited view, you can still infer larger truths, sense structures that extend beyond your direct experience. Maybe the cosmic horizons are just the universe's way of reminding you that partial knowledge can still be meaningful, still be beautiful. In the very far future, if accelerated expansion continues, each bound group of galaxies will become its own little island universe, cut off by event horizons from all others. For hypothetical observers, then, the evidence of expansion, of the cosmic microwave background, of distant galaxies, might fade beyond detectability. They might conclude they live in a quiet, static cosmos and never suspect the grand story we're tracing tonight. You, here, now, exist in an era uniquely privileged for cosmology. The particle horizon is large. The event horizon has not yet stolen too much from view. The sky still carries readable clues about both the distant past and the far future. This is your window, wide enough to glimpse the fire of the beginning and the outlines of possible ends. You exhale. The idea of horizons limits you cannot cross. Regions you cannot know could feel claustrophobic, but perhaps it also brings a certain peace. There are things the universe has simply placed beyond your reach, not because you're not clever enough, but because that's how space-time itself works. You are free, in a way, to focus on the part of the cosmos that is within your light cone, the finite sphere where your life unfolds. Above you, galaxies slip silently toward and away from these horizons, indifferent. Below you, the mattress holds you steady. Between those scales, you are a small, bright point of awareness, watching as the universe draws quiet circles around what you can see and what you can only imagine. Maybe the universe loves these invisible boundaries because they give shape to perspective. Without horizons, there would be no here and there, no now and too late. With them, each moment and each view becomes specific, unrepeatable like tonight, and this breath, inside your own private bubble of stars. You're floating again in that slowed down future. But this time, you aim your attention not at the vast, cold background, but at the actors that still burn and bend and shape the night. The last stars, the dark hearts of galaxies, and the strange way even they eventually fade. You begin close to home, with a star like the Sunday right now. It glows a steady white gold, fusing hydrogen into helium in its core. You can almost feel that warmth on your face when you sit by a window in daylight, a gentle pressure of photons that have been fighting their way outward for hundreds of thousands of years. That very ordinary warmth is powered by a very simple rule. Under enough pressure and temperature, light elements fuse into heavier ones, releasing energy. In your mind, you fast forward. The sun exhausts the hydrogen in its core. The fire in the center falters. Gravity, which has always tried to pull everything inward, begins to win. The core contracts, heats, and ignites new layers of fusion in shells. The outer layers puff up, turning the star into a red giant, huge, cooler on the outside, but blazing within. If you could stand on some distant rock and look at it then, the sun would be a swollen, ruddy lantern, filling much of the sky, bathing everything in a dim, warm glow. Eventually those outer layers drift away, forming a delicate planetary nebula. Shells of glowing gas expanding into space like a soft, luminous exhale. What's left in the center cools and collapses into a white dwarf. A hot, dense ember about the size of Earth, but with half the sun's mass. No more fusion burns there. It shines only with stored heat, slowly radiating its energy away into the dark. You zoom outward and see this story playing out billions and billions of times. Massive stars die more dramatically, in supernova explosions that briefly outshine entire galaxies. Their cores collapse into neutron stars or black holes, leaving behind shockwaves that seed new generations of stars. Smaller stars die more quietly, slipping into white dwarfhood. The universe's stellar population slowly shifts, from bright, young, blue stars to dim, old, red ones, then to a scattering of glowing embers. You glide through a galaxy long after its peak of star formation. The spiral arms have lost their fresh blue sparkle. Instead, they're populated mainly by long-lived red dwarfs and white dwarfs cooling in the dark. Here and there, you see a supernova, maybe triggered by a white dwarf stealing matter from a companion star, but such fireworks are rare now. The galaxy feels like a city at 3 a.m., a few lights still on, but most windows dark. Even so, gravity keeps working in the background. Stars migrate through the galaxy, pulled by subtle tugs from neighbors, from spiral arms, from dark matter. Some drift into the central regions, where a supermassive black hole waits. Others are bumped out into the halo or even flung into intergalactic space. You turn your attention to that central black hole, the quiet monster at the heart. In your imagination, you approach the event horizon, the boundary beyond which not even light can escape. You never cross it. You just hover near, where the physics is still something our equations can describe. The black hole doesn't shine on its own, but gas and dust spiraling into it form an accretion disk, heating up as they fall in, radiating like a hot, spinning halo. If you could listen, you might imagine a low, deep rumble here. Not a real sound, but the sense of gravity at its most intense, warping time and space. As the universe ages, more and more matter ends up in such remnants. White dwarfs, neutron stars, black holes. Collisions and mergers feed the central beasts. Gravitational waves, subtle ripples in space-time, carry away energy when black holes and neutron stars collide. A quiet shudder in the fabric of the cosmos. You fast forward again, beyond even the time when most stars are born. Now the universe has entered the era where stellar death dominates. White dwarfs cool, their light fading from white to red to infrared and beyond. Neutron stars, once born as intensely hot, dense remnants, radiate away their heat and spin down. The night, wherever there is an observer, grows visibly poorer in bright, sharp pinpoints. In your inner vision, you pick up one white dwarf, hold it between mental fingertips. At first, it's still hot and bright, but with no new energy source, it must cool. Over truly enormous timescales, It becomes a black dwarf, a term we use more as a prediction than an observation, because the universe isn't old enough for any to exist yet. A black dwarf is an ember that has lost its glow, a lump of carbon and oxygen at near zero temperature, radiating so little that it's effectively dark. You scatter billions of such objects through space in your mind. Black dwarfs, cold neutron stars, rogue planets, chunks of rock and ice, all drifting under the faint pull of gravity and the even fainter drizzle of background radiation. Between them, black holes sit as the ultimate sinks, swallowing whatever happens to stray too close. Then you turn your attention to the black holes themselves. For a long time, they seem utterly permanent, but quantum mechanics, mixed carefully with general relativity, suggest they aren't. You imagine virtual particle pairs flickering into existence near the event horizon, one falling in, one escaping. To a distant observer, it looks as though the black hole is emitting radiation, losing energy, and therefore mass. This is Hawking radiation. For stellar mass black holes, the timescale for evaporation is absurdly long, far longer than the current age of the universe. For supermassive black holes, it's longer still. But you have all of imaginary time tonight, so you wait. Slowly, almost imperceptibly, the black hole shrinks. As it becomes smaller, its temperature rises, and it emits more radiation. At the very end of its life, it radiates furiously, then disappears in a final burst, leaving behind only a thin spray of particles and photons. You watch this happen over and over in the deep future, like old bonfires finally hissing out their last sparks. When the massive black holes are gone, the universe is left with only lightweight particles and low-energy radiation, the residue of all that ever happened. The gravitational wells have flattened. Space-time has relaxed into something like a featureless plane. Throughout this whole journey, from the steady burning stars of today to the black dwarfs and evaporating black holes of tomorrow, one principle has been at work. The universe is moving from states where energy is concentrated and can do work to states where it's spread out and can't. Stars are engines. They turn nuclear binding energy into light and heat, powering complexity. Remnants are memories. They store what's left until even that memory fades. You lie there, listening to your own body, which is itself an intricate pattern of energy flows. Heat from metabolism, electrical pulses in nerves, pressure waves in blood. All of those depend on gradients, differences between inside and outside, hot and cold, charged and neutral. In a universe heading toward greater and greater uniformity, these little pockets of imbalance are precious and temporary. Maybe, as you think of stars and black holes in the far future, you feel a quiet kinship with them. Like a star, you burn through stored energy in a finite time. Like a black hole, you gather memories and experiences into a dense core only you can fully see. And like both, you are part of a larger pattern in which beginnings and endings are not failures, but transformations. Hydrogen to helium, star to remnant, remnant to radiation, order to gentle simplicity. The long-term fate of stars and black holes might sound lonely, but there's another way to hold it. As the universe's way of completing each story it starts. No star is left half-formed. No black hole remains forever unchanged. Everything that can happen, given the laws of physics, eventually does. The cosmos tidies up after itself, not with a broom, but with time. As you slip closer to sleep, you might let a simple reflection rest in your mind. You are living in an era when stars are still plentiful, galaxies still bright, black holes still whispering quietly rather than raging or vanishing. You get to see the universe while its engines are still running. And when those engines finally stop, trillions upon trillions of years from now, the embers and shadows that remain will still be part of the same great unfolding. Maybe the universe just loves to turn every flame into a memory, every memory into a whisper of radiation, and every whisper into a background hum, a lullaby for whatever, if anything, might still be listening. You're back here now, not in the far future, not at the Big Bang, not at the edge of a cosmic horizon, just on your bed, in your room, on this very ordinary night, on a very ordinary planet. After all that drifting through extreme times and distances, it's almost a relief to feel the smallness of your own body again. The weight of your head on the pillow, the gentle rise of your chest, the way the blankets press against your skin. The universe is expanding. We've traced that story across galaxies and eons. But what does that expansion mean here, where you actually live? You start by zooming out just a little. You picture Earth from above. Blue oceans, white cloud swirls, dark continents. You feel the planet's gravity pulling you toward its center, a steady downward tug you never consciously notice. Earth orbits the Sun. The Sun orbits the center of the Milky Way. And all of that sits inside a small cluster of galaxies called the local group. Then you remember, in all our talk of expansion, we said that some things opt out. The local group is one of those things. Gravity here is strong enough to hold the Milky Way and its neighbors together, even as the universe expands on larger scales. Andromeda, the nearest big galaxy, isn't receding from us with the flow of expansion. It's actually moving toward us, pulled in by mutual gravity. On that scale, the cosmic river runs one way, but local currents swirl and eddy in their own directions. You imagine floating between the Milky Way and Andromeda. In your mind's eye, they're two great pinwheels of stars facing each other in the dark, slowly inching closer over billions of years. Around you, the wider universe stretches. More distant galaxies drift apart, their light reddened by expansion. But here, in this tiny corner, gravity writes a different line of the story. Zoom in further, back to your solar system. The sun's gravity wraps tightly around its planets, asteroids, comets. The expansion of space doesn't pry Earth 1 millimeter farther from the sun in any way you could detect. The electromagnetic forces inside your body, the chemical bonds in your cells, the pressure of your mattress against your skin, all of these are unimaginably stronger than the feeble effect of cosmic expansion on such small scales. There's something quietly reassuring about that. Space can stretch between galaxies, but it can't easily stretch you. You lie there, as stable as you ever are, while the universe breathes around you on scales so huge that they might as well be another reality. Still, even if you don't feel the expansion in your bones, you do live inside its consequences. The very fact that you can see distant galaxies at all, that their light arrives reddened and faint, that the cosmic microwave background glows at just a few degrees above absolute zero. These are expansions, fingerprints. You close your eyes and imagine the sky not in visible light, but in microwaves. Suddenly, every direction glows with a faint, almost perfectly uniform warmth. The afterglow of the hot, early universe, cooled and stretched by billions of years of expansion. Sensitive instruments on satellites have seen this glow. They map tiny temperature ripples in it, patterns that tell us about the universe when it was young. If your skin could feel microwaves the way it feels sunlight, you'd notice a very faint, cool bath of radiation washing over you all the time, coming from every direction. You're wrapped in that relic of expansion even as you sleep. The universe's past is not out there somewhere. Its history is literally touching you, gently, as a drizzle of photons. You open your eyes again in your imagination and look at the ordinary night sky. Maybe you've done this for real. Stepped outside, let your pupils widen, felt the air on your face while you stare upward at stars that feel almost close enough to touch. What you're really seeing is layers of time and distance stacked on top of your everyday life. Some of those stars are tens, hundreds, thousands of light years away. Their light left long before you were born, before your grandparents were born, before your language even existed. If you switch to a telescope and go deeper, you start to see galaxies whose light left when dinosaurs walked on Earth, or earlier still. Some galaxies show you the universe as it was when it was half its current age, or a quarter. You are, in a very literal sense, looking along the slope of expansion, backward in time, right from your backyard or balcony. And yet, as your eyes adjust in the dark, you also notice how small your own sensory range is. You can't see the infrared glow of dust, the X-ray flashes from black hole accretion disks, the radio whispers from cold hydrogen clouds. You can't feel the tiny changes in space-time as gravitational waves pass through you. You are immersed in a universe full of signals you will never directly sense. So you build instruments, mirrors, and antennas and detectors cooled almost to absolute zero that extend your nervous system outward. Telescopes stacked on mountaintops and orbiting in space become extra eyes. Gravitational wave observatories become extra ears for ripples in space-time. Particle detectors buried deep underground become extra skin, feeling the rare touch of ghostly neutrinos. In a quiet way, that means you are already bigger than your body. When we say we measured the expansion rate with supernovae, or we mapped the cosmic microwave background, that includes you. if you choose to claim it. You didn't sit at the telescope or launch the satellite, but you're part of the same curious species that did, and the knowledge flows into you as surely as starlight flows into your eyes. You think about time now. On human timescales, the universe's expansion is glacial. Tomorrow, your room will look the same. Next year, the Milky Way stars will hold their familiar patterns. Even if you lived for 1,000,000 years, you'd barely see the shapes of constellations shift. Your life is a thin slice through a very slow movie. But psychologically, your sense of time can stretch. Lying here, you can let your awareness run backward and forward along the cosmic timeline, from Big Bang to possible heat death, from the formation of the first atoms to the evaporation of the last black holes. Your body occupies decades. Your mind can imagine trillions of years. In that sense, your consciousness is already operating on cosmic scales, even though it's rooted in a soft, finite brain. You listen to your own heartbeat. Each beat, a little pulse of ordered motion ions crossing membranes, muscles contracting, blood moving. All of that is powered by chemical energy that ultimately traces back to stars, to the sun now, to earlier stars that forged the heavy elements in your body. The expansion of the universe set the conditions for those stars to form when and where they did, which in turn set conditions for planets, for life, for you. So even if expansion doesn't tug at your atoms directly, it's woven into the deep story of why you exist in this particular epoch. In a much denser, younger universe, there were no galaxies, no heavy elements, no planets. In a much older, more diffuse universe, there might be no bright stars left to bathe planets in useful light. You live in a wide middle chapter where the universe is just the right age for complexity and curiosity. Maybe that's the most personal way to feel cosmic expansion. Not as a force stretching you, but as a timeline that has placed you here, now, between a hot beginning and a cold end, with just enough structure around you to build a life and ask questions. As your breathing slows even more, you might let a simple thought settle. You are a small, temporary pattern in an expanding universe, but you are also the universe, looking at itself from the inside. The same physical laws that stretch space between galaxies also govern the chemistry of your neurons. When you wonder about the cosmos, it's not something separate you're investigating. It's a part of the cosmos briefly becoming aware of its own story. Maybe the universe just loves this kind of loop. Expansion shaping stars, stars shaping planets, planets shaping life, life shaping thoughts, and thoughts turning back to contemplate expansion again, late at night, somewhere in a quiet room. You don't need to hold the whole picture in your head. You don't need to solve anything. It's enough to know that you are safely nested inside this vast process, held together tightly by local forces, bathed gently in ancient light, drifting with your galaxy through a universe that keeps unfolding whether you're awake or asleep. For tonight, your job isn't to measure the expansion or predict the end. Your job is simple. Feel your own small gravity. Let your thoughts widen as far as they want to go, and then let them soften and blur, like distant galaxies fading into a calm, dark sky. You're very still now. The room is dim. The sounds around you have faded into background hum, and after touring beginnings and endings and distant horizons, you find yourself in a quieter place, not asking how the universe behaves, but what does it all mean for you? You close your eyes and imagine the universe not as a timeline or a pie chart, but as a pattern. At first, it looks like the cosmic web you've seen in your mind before. Filaments of galaxies, knots where clusters live, huge cavities of almost empty space. If you zoom in, those filaments start to resemble something else, you know. The tangle of neurons in a brain, or the branches of trees, or the veins in a leaf. You move smoothly between these scales. One moment, you're gliding through a supercluster, filaments glowing faintly like strands of spider silk. The next, you're inside a forest at dusk, looking up through branches etched against a darkening sky. The crunch of leaves under your feet, the smell of earth and bark, the soft chill on your cheeks, all of it feels eerily similar to drifting through a galactic web, but with different senses engaged. The universe loves certain patterns, branching, clustering, waves, the same mathematics that describes ripples in the early universe. Tiny quantum fluctuations stretched by inflation, later amplified by gravity, also describes ripples in water, sound in air, and even the distribution of notes in a song. The power spectrum of cosmic structure, the way fluctuations of different sizes contribute to the overall pattern. echoes the way vibrations combine in a musical chord. Different details, same underlying idea. Complexity built from simple rules, repeated over and over. You think of atoms arranging into molecules, molecules into cells, cells into organs, organs into bodies, bodies into societies. Each level shows patterns, spirals in seashells, logarithmic spirals in galaxies, fractal branches in rivers and blood vessels. The shapes are not identical, but they rhyme. Maybe the universe doesn't copy-paste. Maybe it improvises around a small set of favorite themes. And yet, while patterns repeat, individual things do not last. Every star we've talked about will eventually die. Every galaxy will change shape, collide, or fade. Even apparently stable quantities like the fine structure constant that sets the strength of electromagnetism are things. Some theories allow to vary over vast times or in different regions. We don't currently see strong evidence that they do vary, but the possibility alone reminds you the rules you take for granted might themselves be part of a larger, changing story. Impermanence is not just a human problem. It's built into cosmic evolution. You've walked through heat death, big rip, big crunch, black hole evaporation. You've seen how entropy grows, how gradients flatten, how structures unravel. It can be tempting to see this as a kind of universal tragedy, a story where everything beautiful is doomed. But lying there, you can flip the perspective. Instead of thinking everything ends, so it's meaningless, you might think everything ends, so it's precious. Stars shine because they're far from equilibrium. Life exists because the universe is temporarily uneven. If the cosmos were perfectly still and unchanging, it would be simple, but it wouldn't be interesting. You listen to the small sounds around you. Maybe a distant car, a fridge humming, leaves outside brushing against each other in the wind. None of those sounds will last more than a moment, but they weave together into the texture of this night. In the same way, galaxies colliding, stars being born, planets cooling, minds wandering, all of those are temporary textures on the larger fabric of space-time. The factual backbone beneath this reflection is simple. The equations of general relativity and thermodynamics tell you that the universe evolves. It started denser and hotter. It will likely continue expanding and cooling, or else reverse and collapse. Along the way, energy flows from more ordered to less ordered configurations. That's the law. The poetry is what you choose to feel about it. You picture, again, the cosmic microwave background, the all-sky baby picture of the universe. Its tiny ripples are nearly scale invariant, meaning the fluctuations have about the same strength on many different length scales. That simple, almost patternless noise was enough, under gravity, to grow into the web of galaxies you imagined earlier. From near uniformity, structure emerged. From structure, stars. From stars, heavy elements. From those, chemistry and life, and eventually you. Now imagine those patterns fading in the far future. The web thins, stars burn out, black holes evaporate. The universe smooths itself back toward uniformity. The arc is clear. From simple to complex, towards simple again, but a different kind of simple. Not a rewind, but a one-way journey through configuration space. In that arc, every pattern is temporary, a wave crest in a larger sea, including the pattern of your own thoughts. Neurons fire, strengthen some connections, weaken others, memories form and fade, moods shift. Whatever worries or hopes you're carrying tonight, they too are impermanent ripples in a brain that is itself a temporary pattern in an expanding universe. There can be comfort in that. If everything is absolutely permanent, every mistake feels carved in stone. If nothing is permanent, then there's room for change, for forgiveness, for letting go. The universe doesn't hang on to old structures forever. It recycles them. Stars die to seed new stars. Massive stars explode to seed planets. Planets erode to feed atmospheres and oceans. Life ends and returns its materials to the environment. On cosmic scales, you're participating in the same cycle, just at a smaller, more intimate level. You let a quieter image arise now, a night far in the future, when the sky has grown mostly dark. A lone observer, if any exist, looks up and sees only a few faint stars, or perhaps none at all. No obvious galaxies, no clear evidence of expansion, no cosmic microwave background in reach of their detectors. For them, the universe might seem still, eternal, unchanging. But you know, from your vantage point, that the stillness is an illusion. There is still radiation spreading, particles drifting, space-time evolving. Entropy is still increasing, just more slowly, more subtly. The universe is still doing its thing. It's just that most of the obvious drama has already happened. The quiet is not the absence of process. It's process reaching a kind of calm saturation. You compare that to your own inner life. When you're younger, everything seems to change quickly, new experiences, new emotions, sharp highs and lows. Later, for many people, things feel more settled on the surface. But under that apparent stillness, your cells continue turning over, your brain continues rewiring, your thoughts continue flowing. Stillness is rarely truly still. It's just motion too gentle to feel. Thinking about cosmic impermanence and stillness doesn't give you a rule book for how to live, but it can gently tilt your perspective. Maybe the lesson is something like this. Patterns are fleeting. Their fleetingness is what allows new patterns. And you are one of those patterns, real and valid while you exist. You are not less important because the universe will one day be cold. The chemical bonds in your body are not less real because protons might decay in the distant future. Importance and reality live in the present configuration, in the relationships and experiences that exist now, not in how long they last compared to the age of the cosmos. You listen to your breath again. In, out. Each inhale is a small local decrease in entropy, oxygen molecules going from the air into your bloodstream, fueling organized processes. Each exhale releases heat and carbon dioxide back into the environment. Without the larger trend of entropy increasing, this small local reversal couldn't happen. Life uses the broader arrow of time as a kind of slope to run downhill on, doing intricate things on the way. So when you think of the expanding universe and its ultimate fate, you don't have to choose between despair and denial. You can hold both the scientific picture patterns forming, changing, dissolving, and a softer, more personal understanding that your thoughts tonight are part of that same play of patterns. Maybe the universe just loves to draw temporary shapes on its own canvas. Galaxies here, nebulae there, a few billion minds wondering about it all, and then, when their time is done, it wipes the slate gradually clean and starts tracing something else, or simply lets the drawing fade into quiet. Right now, you are one of those shapes. Impermanent, yes, but also intricate, aware, capable of feeling awe at the whole process. That combination, small and aware, is rare, as far as we know. It's more than enough reason to take one last slow breath, let your muscles loosen, and let your thoughts dissolve for a while into your own private version of cosmic stillness. You're so close to sleep now that every thought feels like it has to move in slow motion, as if the air inside your mind has thickened. You've walked through the birth of space and time, watched galaxies drift apart, followed stars to their deaths, hovered over black holes, and peeked at the far futures the universe might choose. Now, for this last stretch, you let all those details soften. You don't need to recall equations or numbers. You just hold a simple, steady sense. Whatever its exact path, the universe is unfolding according to rules that keep working, quietly, everywhere. You picture the different endings you've visited laid out like pages on a table. On one page, the universe fades toward heat death, a long, cool hush where everything slows and smooths out. On another, phantom dark energy tears space apart in a big rip, a sharp full stop written in runaway expansion. On a third, gravity pulls everything back into a big crunch, maybe followed by a bounce into something new. There are other sketches too, subtler modifications, exotic fields, quantum twists at the beginning and the end. One by one, you imagine sliding those pages on top of each other until they blur into a single image. Details disappear. What remains is the outline of a story that feels the same in every version. The universe begins in a state unlike today. It changes. Structures arise. Structures pass. And the laws that steer this whole process stay astonishingly consistent. You drift up above your imagined table and look down. From this height, you can't tell which ending is printed on top, but you can see that every page is written in the same handwriting. Gravity, quantum fields, thermodynamics, the speed of light, the way space-time curves, all of it keeps its character from frame to frame. The universe may not tell you which finale it prefers yet, but it keeps performing the play with a kind of ruthless reliability. You breathe in gently and feel that reliability in your own body. The The same constants that set how stars shine also set how atoms in your neurons interact. The same expansion that stretches light from distant galaxies also cooled the early universe enough for atoms to form at all. The arrow of time that will someday carry stars to their deaths is the same arrow that lets your memories line up in a meaningful order. You're not separate from the story. You're embroidered into it. For a moment, you let yourself imagine a distant, far future observer, maybe living in a small island galaxy long after most others have slipped beyond its horizon. Or maybe something stranger, some form of awareness we can't yet picture. They look up at a thinner sky and piece together their own version of cosmic history from the clues available to them. Their picture might be incomplete in ways yours is not, and complete in ways yours can't be. Yet, underneath, the same physical principles guide their thoughts, their chemistry, their stars. It's a quiet reassurance. Understanding will always be limited, but the thing being understood remains steady. Whether or not anyone is there to measure it, hydrogen fuses the same way. Gravity curves, space-time the same way. Light moves at the same speed through the same vacuum. Physics hums on, indifferent and dependable. And that brings you, finally, back to yourself. You are lying in a small patch of space-time on a small, rocky planet, at the edge of an ordinary spiral galaxy, in a universe whose expansion you can barely feel and yet have learned to describe with remarkable precision. You've borrowed starlight to grow your body, borrowed oxygen and carbon from long-dead stars, borrowed knowledge from generations of minds who stared at the same sky. Now, for a little while, you're allowed to set all of that down. Here is where the story slows. You picture the room around you from the outside. 4 walls, a ceiling, a floor, maybe a window with a faint glow from the street or the moon. Outside the walls, a city or a town or a quiet countryside. Outside that, continents, oceans, weather systems swirling. High above, a thin atmosphere, then the vacuum of space, satellites tracing smooth loops. Farther still, the sun, the planets, the dark between stars, the arms of the Milky Way, the web of galaxies, the large-scale structure of the cosmos. All of it is doing something right now. Stars are fusing, gas clouds are collapsing, black holes are spinning, dark matter is tugging, dark energy is stretching, radiation is streaming through the void. Countless processes, all obeying the same simple set of rules, all ticking along at their own pace. You let that image expand until it feels too big to hold, then you shrink it back down to this. The universe is still here, quietly working while you sleep. You don't have to monitor it. You don't have to decide which ultimate fate is true tonight. You don't have to hold the whole 13.8 billion years in your thoughts. The expansion will continue or change without your supervision. Galaxies will move exactly as they're meant to, whether or not you remember their names. What you can do is let your nervous system step back from full alert, the way a telescope parks itself and closes its dome at the end of a long night of observation. You can let your muscles loosen, one by one, like galaxies slipping gently out of each other's gravitational reach. You can let your thoughts thin out, like the bright points in a sky where the lights are slowly dimmed. Breathe in. You imagine drawing a small piece of the universe into yourself, air shaped by the planets, gravity enriched by ancient stars, cooled by cosmic expansion. Breathe out. You give a little warmth back, a tiny contribution to the great rise of entropy, a whisper of heat joining the background around you. If worries float through, you can treat them like distant galaxies. You notice their light, you acknowledge their motion, and you let them drift out toward the horizon of your attention, where they grow fainter and redder, and finally slip beyond immediate reach. They still exist, but they don't have to fill your whole sky. In the darkness behind your closed eyes, you might picture a final scene, the camera pulling slowly back from your sleeping form, out through the roof of the building, into the night air. You grow smaller as the city shrinks to a cluster of lights, then a dot on a spinning planet, then a mote circling a star, then a spark in a spiral arm, then a barely visible feature in a vast, expanding universe. From that altitude, your entire life is a brief flicker, and yet the camera lingers. It doesn't hurry past. It acknowledges that, for a short, finite time, in one tiny corner of space-time, there is awareness you watching the universe, feeling feelings about it, and then finally, letting go into rest. The laws that govern supernovae and black holes and cosmic expansion will keep running without you for a while. You are allowed to hand the universe back to itself for safekeeping. It has managed just fine for billions of years. It will manage through the night. So you let your breathing find its own rhythm, like the slow, nearly invisible rhythm of cosmic expansion. And you let the weight of your body sink into the mattress as if gravity were tucking you in. Thoughts soften at the edges. Sentences break apart into fragments. Images dissolve into quiet. Somewhere, galaxies are still drifting. Somewhere, new stars are lighting. Somewhere, the future fate of everything is being written in the silent language of physics. Here, there is just you, this moment, this breath, and a universe that is vast enough to contain every possible future, and calm enough right now to let you sleep.